Hi everyone, in this lesson, we are going to discuss about the second part of magnetic property of coordination compounds. In content, we will cover diamagnetic correction, orbital contribution, and magnetic properties of lanthanides complex. Diamagnetic correction. Although, in the classical theory, the susceptibility per gram atom equation gives an idea of diamagnetic susceptibility, in practice it is of little value, because of uncertainty involved in evaluating the electron orbit radius. From measurements on a very large number of compounds, Pascal concluded that the susceptibilities could be represented by the expression chi_m is equals to summation Na chi_a plus summation lambda, where Na is the number of atoms of susceptibility. Lambda is a constitutive correction, depending on the nature of the bonds between the atoms. In this expression, chi_a is not the theoretical atomic susceptibility, but is a purely empirical constant, derived from the measured susceptibility. We take an example from Pascal, to determine the value of chi_c. Here we will take example from aliphatic series. For hexane, the value of chi_m is equals to 79.6 into 10 raised to power minus 6. For octane, the value is 103.7 into 10 raised to power minus 6. So, the difference between these two is equals to 2 into 12.05 into 10 raised to power minus 6. For decane, the chi_m value is 129.7 into 10 raised to power minus 6. And the difference between octane and decane is 2 into 13.0 into 10 raised to power minus 6. From these data, the mean value of chi_CH2 is minus 12.35 into 10 raised to power minus 6. Then, chi_C is equals to chi_CH2 minus chi_H, which is equal to minus 12.35 minus 2 into 3.05 into 10 raised to power minus 6. So, chi_C becomes minus 6.25 into 10 raised to power minus 6 CGS units. The value of chi_hydrogen was obtained independently from measurements on hydrogen. Pascal's constants for some atoms, ions, and species are given in the second table. For hydrogen, chi_dia is equals to minus 2.93. Carbon, minus 6. Nitrogen in open chain, it is minus 5.57. For nitrogen in ring, minus 4.61. For nitrogen monoamide, minus 1.54. Nitrogen diamide, or Illinois, minus 2.11. For certain bonds types, Pascal's experimental data fitted well with his empirical equation, only when he introduced certain corrections. These are called Pascal's constitutive corrections. Thus, in the compounds containing C double bond, he observed that molar diamagnetic susceptibility values, based on atom constants, has to be corrected by plus 5.5 into 10 raised to power minus 6 CGS units, to get a good fit with the experimental values. Similarly, compounds containing the C triple bond has to be corrected by plus 0.8 into 10 raised to power minus 6 CGS units. The calculation of Chi-M for some common ligands are shown here. See the first example. For acetate, atom correction for 2 carbon atom is equals to minus 12 into 10 raised to power minus 6. For 3 hydrogen, it is minus 8.79 into 10 raised to power minus 6. For 2 oxygen, in carboxylate, it is equals to minus 7.95 into 10 raised to power minus 6. Constitutive correction is summation lambda is equal to 0. So, the atomic correction summation Na Chi-A is equal to minus 28.74 into 10 raised to power minus 6 CGS unit, compared to experimental value of minus 30 into 10 raised to power minus 6 CGS unit. Orbital contribution. First one is orbital contribution from e.g. orbital set. Form orbital angular momentum to contribute, and hence, for the paramagnetism to differ significantly from the spin-only value, the orbital in which electron resides must be transform the orbital into an equivalent and degenerate orbital by a simple rotation. It is the rotation of electrons which induce the orbital contribution. In a free ion, the 5d orbitals are degenerate, and some orbitals can be transformed into one others by rotations. The figure illustrates that a 90 degrees or 45 degrees rotation about z-axis transform dxz to dyz and dxy to dyz, or dxy to dxz and dxy to dx square y square orbitals, respectively. In all octahedral complex, due to crystal field splitting, the 5d orbitals split into 2 sets of orbitals of different energy, that are T2g and Eg. The energy barrier between these 2 sets restricts the orbital magnetic moment of the electrons. The degeneracy between the dxy and dx square y square orbitals is also removed. That transformation of dxy to dx square y square is now restricted. In an octahedral field, dx square y square and dz square orbitals are degenerate, but the shapes of these orbitals are such that one is not transformable into the other by rotation. Thus, e.g. orbital set in octahedral geometry cannot generate any orbital magnetic moment. Hence, the dx square y square and dz square orbitals means, e.g. orbital set, are known as non-magnetic doublet. These orbitals are non-magnetic in the sense of orbital magnetic moment. However, spin magnetic moment is still generated by these orbitals. Second one is orbital contribution from T2g orbital set. The T2g set of orbitals means dxy, dxz, and dyz are similar in energy, shape, and symmetry. For example, if the dxy and dyz orbitals are degenerate, moreover, the dxy orbital can transformed into dyz orbital, by rotating it through 90 degrees about the z-axis. There is a further factor that needs to be taken into consideration. Number 1, if all the T2g orbitals are singly occupied, an electron in dxy orbital cannot be transferred into dyz orbital, because it already contains an electron having the same spin quantum number as the incoming electron. Number 2, if all the T2g set of orbitals are doubly occupied, the transfer is not possible. Thus, only configurations which have T2g electron other than 3 or 6 electrons make orbital contributions to the magnetic moments for octahedral complexes. Thus, octahedral complexes with D1 and D2 configurations will have orbital magnetic moment, but the octahedral complexes with D3 configuration will not. 2 orbital contribution from T2g orbital set. The expected orbital contribution in high-spin octahedral or tetrahedral complex with any of the D1 to D10 complexes is shown here in this table. This table also lists the ground state terms corresponding to the Dn configurations. When an electron distribution take up, then only one arrangement is possible, and the corresponding ground state term is singlet A. When 2 arrangements are possible, ground state term is doublet E, and for 3 arrangements, ground state term is triplet T. In a term symbol, the left-hand superscript denotes the spin multiplicity, and the right-hand subscript G indicates gerade. It is clear that metal ions having A and E ground state terms don't show orbital contributions. However, those having T ground state terms are expected to show orbital contributions to the effective magnetic moment. This explains why the effective magnetic moment for tetrahedral nickel 2+, octahedral cobalt 2+, and octahedral Fe2+ complexes is higher than the spin-only value. Let us consider nickel 2+ means D8 complex as a free ion. The total magnetic moment mu L plus S is calculated to be 4.47. In octahedral D8 complex, the orbital contribution is 0. On the contrary, D8 tetrahedral complex will have contributions from the orbital magnetic moment. Hence, although both the complexes have 2 unpaired electrons, the hexa-aqua-nickel 2+ complex has magnetic moment close to the spin-only value, but the magnetic moment in tetrachloro-nickel complex is higher than the spin-only value. Magnetic properties of lanthanide metal complex. The lanthanides belongs to the inner transition series. These elements are generally trivalent, having electronic configuration palladium 4F, 0 to 14, 5s2, 5p6. The paramagnetism in these elements arises from the 4f electrons. These electrons are effectively shielded from external influence by filled 5s and 5p subshells. Evidence that 4f electrons responsible for the paramagnetism are relatively free from external influence is given by the facts that the lanthanides are remarkably alike chemically, and that their absorption bands and magnetic susceptibilities are little affected by change of ionic environment, as by change of compound or of solvent. The crystal field effect in lanthanides is about 1 by 100 of that observed in the first transition series. This suggests that, for lanthanides, the spin-orbit coupling constant is quite high, that means spin-orbit coupling is much higher than ligand field splitting, so that the L and S vectors couple effectively to give the J vector. Thus, for lanthanides, J is a good quantum number. As we realize now, this is simply equivalent to assuming the multiplets all wide, compared to kT. The magnetic moment will be given by the following equation. Mu J is equals to under root J into J plus 1 G beta, where G is equals to 1 plus S into S plus 1 plus J into J plus 1 minus L into L plus 1 divided by 2J into J plus 1. On simplifying this equation, we get G is equals to 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1, where J is equals to L plus S to L minus S. For the calculation of G value, we use minimum value of J for the configurations having up to half-filled f orbitals. It explains J is equals to L minus S for configurations F0 to F7. Maximum value of J is used for configuration with more than half-filled f orbitals. It explains J is equals to L plus S for the configurations F8 to F14. For F0, F7 and F14, L is equals to 0. Hence, mu J becomes mu S. Now let us calculate land factor G and mu J for praseodymium 3+ ion. Praseodymium 3+ has electronic configuration xenon 4F2. The ground state from Hund's rule is shown here. Thus, total spin quantum number S is equals to 1/2 plus 1/2 is equals to 1. Spin multiplicity 2s plus 1 is equals to 3. Total angular momentum number L is equals to 3 plus 2 is equals to 5. J can be 6, 5, 4. Now, G is equals to 3 by 2 plus 1 into 1 plus 1 minus 5 into 5 plus 1 divided by 2 into 4 into 4 plus 1. G becomes is equals to 0.8. Now, calculate mu J. Mu J is equals to 0.8 under root 4 into 4 plus 1 Bohr magneton. On calculating, mu J is equals to 3.58 Bohr magneton. This calculated value is very close to the experimental value, μj, which is, equals to, 3.4 to 3.6, Bohr magneton. Calculated, and observed magnetic moment, for the trivalent lanthanides, are shown here in this table. Land formula fits well, with observed magnetic moments, for all the lanthanides, except, Sm3+, and Eu3+. The magnetism of these two ions, is best studied in combination with, that of promethium, and terbium. As we know that, the energy separation, between the ground state, and the first excited state is, 5 lambda, for Pm3+, 7/2, lambda, for Sm3+, 1 lambda, for Eu3+, and 6 lambda, for Tb3+. Lambda, is the spin-orbit coupling constant, which is about 1000 cm inverse, for all the lanthanides, except, Sm3+, and Eu3+. However, lambda value for Eu3+, and Sm3+, is about 230 cm inverse, that means, the energy separation, between the states, is about 230 cm inverse, for Eu3+, and for Sm3+, is about 840 cm inverse, which is also a small value. The magnitude of separation, between the adjacent states of a term, indicates the strength of the spin-orbit coupling, and in all cases, except Sm3+, and Eu3+, it is sufficient to render the first excited state of Ln3+, thermally inaccessible, and so the magnetic properties are determined only by their ground state. In each of these ions, the J value is higher than that of the ground state, and μJ is expected to be greater than that of only the ground state. Calculated and observed magnetic moment for the trivalent lanthanides. Thank you.